Hey everyone, this is Dr. Walker. This is video 233, Batteries and EMF. Let's start off with a question. How does this happen? You can light up a bulb with a potato. What in the world? Now this picture is not 100% accurate because you cannot light up that kind of bulb with just one potato, but the following picture is a little bit more accurate. If you put several potatoes together, and you connect them, then you can actually light up a very small bulb. But still, how is this possible? Right? For the bulb to light up, you need to have charges flowing through this bulb. How does this happen? Put your thoughts in a comment below. Let's take a look at batteries. So the way batteries work, this is just a very simplified version, but you have chemical reactions within the battery that provide a continuous supply of charges at the positive terminal. So what we're saying is that the chemical reactions here can bring all of these positive charges to the positive terminal so that they can flow all the way in your circuit and go to the negative terminal. So what's happening is that the chemical reactions, they're able to separate the charges within the battery so that once they're separated, then they can flow through the circuit. So what the battery is doing is it's giving the charges energy so that they can flow, so that current can flow in the circuit. This question is just a very simple question to show you that when you do have batteries, that they are your source of voltage, and we've talked about this in the past without mentioning too much about it, but your batteries provide your voltage. And if you put several batteries together, you can amplify your voltage. So in this case, we have 3 batteries, and I'm calling them ideal because we haven't talked about any other more realistic types of batteries just yet. So if we have 3 ideal batteries, what's the total potential difference that we get out of these 3 batteries? What do you think? So it turns out that if they're hooked up like this from negative to positive, negative, positive, negative, positive, that all of the voltages will add up. So 1.5 plus 1.5 plus 1.5, you get 4.5 volts. So your batteries provide voltage. And remember, our definition of potential difference is change in energy per charge. So this goes back to what we just said in the previous slide, that the battery provides energy for those charges to flow through the circuit. Now let's look at EMF. This is slightly different. So EMF is defined as the energy per unit charge provided by a source, i.e. a battery or a generator. Okay, so it sounds like that's what we just said, right? Energy per charge. Didn't we say potential difference is energy per charge? So what's the difference? So the difference is that your battery is going to have an EMF. It's going to provide a certain amount of energy per charge. But by the time the charges leave the battery, they're actually not even going to have as much energy as they had from the battery itself. So the EMF is what's actually provided by the source, but it's not necessarily what you're going to get out of the battery. So in this first picture, I just show a battery connected to a resistor. This battery here is a source of EMF. In the next picture, I have an ideal battery, which is the only type of battery that we've talked about so far. So if you have an ideal battery, then it provides an EMF. And that EMF is equal to the potential difference. All of the energy per charge provided by the source, which is the EMF, is the same as the potential difference that you're getting from that battery that's going to allow the charges to move through the circuit. Where it gets a little bit more complicated is understanding the difference between EMF and terminal voltage. So when you have an ideal battery, the terminal voltage is just the voltage between the 2 ends of the battery. So this would be the terminal voltage. And we can call it delta V, terminal voltage. So we already said that the EMF is equal to the delta V. But what we're saying now is, let's say that you have a battery that's not ideal. Then we're saying, okay, if there's no current, so let's say there's an open switch. We have a resistor here, but we have an open switch. Whenever you have an open switch, then no current can flow in the circuit. So when that's the case, then the EMF provided by this battery, so this is non-ideal battery, the EMF is going to be equal to the terminal voltage when there's no current. And we're going to see in the next slide that when there is current, then the EMF and the terminal voltage will not be the same when you have a non-ideal battery. It's only going to be the same when you have an ideal battery. Just to finish up EMF, since it is very similar to terminal voltage and voltage, it is a voltage. It does have a unit of voltage, so it is measured in volts. So for this section, the EMF and the terminal voltage will not be the same thing because we will deal with non-ideal batteries, but for the rest of the course, we'll go back to the ideal batteries. And whenever you see EMF, you can just think of potential difference. One more thing, the rating of a battery is the battery's EMF. So if you have a battery, let's say a AA battery, right? AA. If you look at that battery, it says 1.5 volts. So that rating on the battery, that is the EMF. So that's the energy per charge that it provides. But once you connect it and once there's a current, then that EMF does not equal the terminal voltage, the voltage that you're actually going to get in your circuit. I think this picture here will help clear it up. I should have had it a little bit sooner, but this really helps to show it. So this is a real, in quotes, or you can say a non-ideal battery. So a more realistic battery. What you see here is in yellow is the whole battery. So the battery has the EMF source, right? It has all those chemical reactions providing the energy per charge. But the battery itself has an internal resistance R. So what that means is that when the charges are flowing, they're going through this little internal resistance, little r, they're losing energy in that internal resistor. So that's why the voltage that you get out of the entire battery, the whole yellow thing is the battery, this is a terminal voltage that you're getting out of the battery. And that is going to be less than the EMF because some energy is going to be lost when the charges go through the resistor. The terminal voltage of the battery is less than the EMF when connected. Let's go ahead and look at and see what is the terminal voltage going to equal. Terminal voltage, delta V, which is this one over here from the two ends of the battery, is going to equal the EMF from the battery that gives us the voltage minus the voltage across the resistor. Can you think about how much voltage is lost across the resistor? Think about Ohm's law, which tells us that I equals delta V over R. And let's just use little r because we're looking at the internal resistance. And solve for delta V, you get IR. Let's call it delta V sub R. That's the voltage across the little resistor. You can always use Ohm's law to find the voltage across a resistor. When there's current through a resistor, there's a potential difference across the ends. So since you're losing energy going across that resistor, you're losing voltage. So minus IR. That's going to be the terminal voltage. You can see that if the current is 0, then the terminal voltage is equal to the EMF. So this slide really sums up what we've been saying for the last few minutes. Let's take a look at an example. Again, this is kind of just a plug and chug example. I just wanted to put it in the your turn so that it could finish up this video without needing a separate video. So this example says a 6-volt battery with an internal resistance of 1 ohm is connected to a load resistor. So the load resistor is just the other resistor that's part of the circuit. If we go back to our previous circuit here, we had a big R, and that was just the load resistor in the circuit, just a regular resistor in the circuit. We're calling it load resistor so that it's not confused between the internal resistance of the battery, which was little r. So find the voltage across the battery terminals, so the terminal voltage, when there's a current of 2 amps from the negative to the positive terminal. So the trick is to identify the variables. Internal resistance, so that's little r, is 1 ohm. We don't know what the big R is in this case. Find the voltage across the battery terminals. We're looking for delta V. We know the current is 2 amps. We're told that it's a 6-volt battery. Remember, in a previous slide, we said the rating of the battery is the EMF of the battery. So 6 volt is the EMF of the battery. So the terminal voltage is going to be equal to the EMF minus I times little r. So it equals 6 minus 2 times 1, it equals 4 volts. So the terminal voltage is 4 volts. So the battery is supposed to give us 6 volts, that's the EMF. But once you connect it to your circuit, some of the energy is lost in the internal resistance. So the terminal voltage is what you're actually getting out of the battery. You're getting 4 volts out of this specific battery that has an EMF of 6 volts. That's all. Be sure to do the practice questions for this video just so that everything makes perfect sense, and I'll see you in the next video.